we don't calculate this, you don't see this again. Standard error, we do, okay? And standard error is the standard deviation of a sampling distribution, okay? So this symbol right here is standard error. Sometimes, oh my gosh, I just kind of like blinked out. I want to say we could see it like that, but I'm kind of doubting myself right now. So let's just stay with this. Let's just stay with this one. So the standard error, and what this is saying, if you look at this, we know this is standard deviation, this symbol right here. And then this one is the mean, right? So it's like it's saying the standard deviation of the mean, okay? So it's really simple to figure out. You just take the standard deviation and then you divide it by the square root of n. Okay, so this is a really simple little, I kind of like call it a conversion. So it's like once we've calculated the standard deviation, or when the standard deviation is given to us, we just do this little conversion and we put it into standard error, okay? Okay, so standard error, I'm not getting, well, this will come back. Okay, so these are just little things that we have to do. And what it's doing actually is making the standard deviation into a smaller unit. Sometimes I like to say it makes it more bite size, okay? And the reason why is another interesting part of the central limit theorem is that as n increases, variability decreases. Let's see. I'll write it. I'm going to insert a text box and I'll type it. As n increases, the variability, oops, variability decreases. And so you'll notice right here, well, let's look at this one because these are actual numbers right here. So the range, we can use the range in this one because just 1 to 10, right? So our range here is 9. Okay, and we know range is a measure of variability. So we could say this range was 9. I'm gonna write it. Oops, or not. Ah. Why won't it? Why? There we go, 9. This range here didn't change in this instance, so it's also 9. But now look at this one, 4.5 to 7.3. And I don't know what the difference of that is. It'd be like 4.3, it'd be like 3. I don't know, it's around 3. Our range has shrunk, right? So our variability has decreased. It's the same with this one here. It's about 3, right? You can notice here, 1 to a king. Now it's gone significantly up from 4.6 to 9.4. So our variability has decreased here as well. And so
the variability,
oh, go ahead.
So the variability is basically the standard deviation getting smaller.
That's that right.
What you're saying? Okay.
Well, yeah, the variability, the variance or the variability, the differences among all of those scores is shrinking. So we can't use standard deviation in this instance. We can't use standard deviation here because that value would be too big. So we're just going to shrink it down a little bit so that it makes more sense for this little guy right here. Let's just say, I don't know what the standard deviation for playing cards is. I don't know that, okay? But let's just, I don't know. Let's just say it was 4, okay? Well, if we went down here and we were still using a standard deviation of 4, let's see, from 4.6 to 8.6 would already be 4. So we're already like moving, we're including the entire distribution with just one standard deviation, one movement. Does that make sense? It, like if we went up 4, we're already way over here. If we went down 4, we'd be way over here. We'd be off the chart. Yeah?
Oh, okay.
I
Yeah.
don't know. Maybe that makes sense.
So sort of.
Okay. Remember, standard deviations in a normal distribution, we're just moving a little bit, right?
Yeah.
So if it was 4, from this 4, it would be way over here, would be 1 standard deviation. And we know in a normal distribution, that's not how that goes. 1 isn't way over here.
No.
Okay.
Oh,
Yeah.
I see.
Okay, maybe that makes more sense.
Yeah.
It's a little, yeah. So what we do is we take it and we divide it by the square root of n, and it just makes it a little bit of a smaller number that makes more sense for what we're working with. Okay.
Okay.
Like I say, it makes it into a little bite size. Okay. All right. So I know it's probably a little confusing on what in the world we're doing, okay? And I promise you it's all going to make sense probably next chapter, okay? So just kind of take this, take it, maybe read over some of the main points and these main words that we have here. And then I promise you in chapter 10, it'll start to make more sense, okay? Or not 10, chapter 9. Okay, so now we have to talk about the T distribution, okay? And this is the T test, the T statistic. This is more commonly done in research, okay? It's not the most common because it's just maybe a little bit too simple, but it is widely used, and you may see it in some of your scholarly articles that you might have to read for another class, okay? So the T distribution, we use the T instead of the Z because we use it when we do not know the population standard deviation. Sorry, I had to close my door. Okay. When we do a Z-test, if you remember from our exam, all of that information was given to you. You were given the standard deviation. You were given the population mean, okay? And that's why it works well with like IQ, right? Because we know the population mean and the population standard deviation. But out in the world, for the most part, we don't know the population standard deviation. We're lucky if we even know the population mean, right? Think of what is the average side effects that we see from the COVID-19 vaccine? I don't know, right? You know, we might start to get an average, like what do they say? Sore arm, headache, things like that. Do we know the standard deviation of that? No way, right? Not at all. If I'm looking at how many potato chips somebody eats when watching the Super Bowl compared to watching news, I don't even know the population mean, let alone the population standard deviation, okay? So we use the t-test when we don't know the population standard deviation, okay? We will know the population mean because that's just where we are right now. I want to see what they used to do a long time ago is just use the estimated standard deviation, right? We would estimate it. And that was okay. And it is okay. And we still do use the estimated standard deviation. But when they were only using that event or that I don't know what I'm trying to say, when they only used that measurement, they had to have very, very large sample sizes. You had to have thousands of people in your study, had to, okay? But now when we have the sampling distribution, we don't need that anymore. Okay, we don't have to have super large samples. Now we know that the magic number is 30. Okay. So the T distribution, well, I'm not gonna really read it because it's in there for you guys, and it really is an interesting story behind the guy that came up with the T distribution. Okay, so you literally can't make this stuff up. If you wrote a book about this guy, you would be like, there's no way you're making that story up. It's not real life, but it is. Okay, so his last name is Gosset. Okay, Gosset. And he was super smart, way, way, way smart. He went to Oxford, and he got a job at Guinness. Okay, like Guinness, like the beer. Okay, he got a job in the brewery at Guinness, and he was quality control. And so what does that mean, right? He sampled the beer. And so I like to think that he was probably really drunk when he came up with this, because I guess I just can't fathom somebody's brain would come up with this on his own. But one day when he was sitting there sampling the beer, and you know, when they sample them, it has to be a really little glass, right? Or like a shot glass, maybe even like a medicine, you know, contain a little thing that they're sampling the beer from. And they're taking this tiny little sample from a huge vat of beer. And one day he was sitting there and he was like, if my sample is so small, how can I be sure that it's truly representative of that big vat of beer? And so he came up with a whole distribution of numbers and a table that is based on the normal distribution depending on how big your sample is. Like, I can't even wrap my head around that. Like, how would he even know how to do that? But I don't know. Obviously, the guy was super smart. Okay. So I'm going to come back to this slide real quick. We'll talk about degrees of freedom in just a minute. Okay. So what we have here is the T distribution. And this guy Gosset came up with this. Okay. We've got a lot of stuff going on. We've got this degrees of freedom over here, and we have all these numbers. Okay. So this is what he came up with. Now let me back out of this and go back to degrees of freedom, because that's this number right here that we're going to use. So degrees of freedom is a mathematical statistic that determines which distribution is appropriate for sample data. Okay, so this is a very weird definition, and I'm going to give a different one in just a minute. Okay, so it's saying it's a concept in mathematical statistics that determines which distribution you're going to look at for the appropriate sample. Okay, for whatever sample data you have. Here's what we need to know, right? Sometimes we're like, who cares about that definition? What do I need to know? Well, it's n-1. Super simple, n-1. So if I had 10 people in my sample, my degrees of freedom is 9. If I had 100 people in my sample, my degrees of freedom is 99. Okay, it's just n, your sample size, minus 1. Now, let me give you a better explanation than this one. And I hope that this makes a little bit more sense, okay? If a true, let's see, let's not say that. Okay, this was always easier when we were in real class because I always had everybody sit down, and you know, by the middle or even about a week into the semester, everybody's sitting in the same chair, right? And it stays that way for the whole semester. And it's like it becomes your chair, right? Well, in my statistics classes, we have computers, okay? And so the same concept, everybody always sits in the same chair day after day after day after day. And let's say those computers or those chairs were numbered 1 through 25. And when I go into that class, the doors were always locked. And we always had to wait for the guy in the computer lab to come over and open the door. And so what happens is everybody kind of lines up in the hallway, waiting to get into the classroom. Now, let's imagine that it's day number 1. They've never been in that classroom before. Now, I know that there are 25 chairs in there. Okay, they don't know that, but I know that. So that's the population, right? We know that there's 25. And let's just say I had a little coffee can, and inside of the coffee can, I had 25 pieces of paper numbered 1 through 25. And let's say Natalia was the first person in line. And I held up that coffee can and I said, draw out a piece of paper. And let's say she reached her hand in and she pulled out a piece of paper, and just to make it easy for my brain, let's say she happened to draw number 1. And so she goes in and I say, okay, you go sit at computer number 1. Now, what happens when she was the first one to draw, she had the widest range of freedom for any value for her to pick. She could have picked 1 through 25. She had 25 degrees of freedom, right? The next person, let's say the next person was Cynthia, okay? Cynthia now has 25 minus 1 options or degrees of freedom for her to choose. So she sticks her hand in and she draws number 2, right? And she goes sits at computer number 2. Now the next person has 24 minus 1, right? Something like that. Does that make sense?
Yeah, it does.
Kind of? Okay.
No, so you keep subtracting 1, basically.
That's exactly right. Okay.
Okay, yeah.
So that's a real life example kind of describing what this idea of degrees of freedom is. Now, let me put it into mathematical terms. Now, this gets a little funky, okay, but just hang in there with me. A true average exists out in the world for whatever. Let's say the number of potato chips eaten during Super Bowl. There has to be a true average that exists. Do you agree with that?
Okay.
Right? I mean, there has to be. I don't know what it is, but there has to be an average of the number of potato chips eaten on Super Bowl Sunday.
Yes.
Okay, so there has to be one, right? So I don't know what it is, but the universe knows what it is, if you want to think of it like that. The minute let's see, I don't know if that example is going to work. Well, let's just go with it. The minute, say, I get research and I found that the average number of people that I researched was 50, I don't know. Now, the next number the next city or the next researcher, that number is going to have to make sense with the equation that ultimately the mean would be accurate, that the average would be accurate. Okay, that I realize now that's probably really far out there. Let's say I know what the average test score was for exam 1.
Mhm.
And let's just, I don't know what it is because I didn't look, but let's just say it's 80. Okay. The minute I get somebody's score, and let's say it was a 30, well, the next number has less freedom to vary. Like, it doesn't have that much freedom. It's going to have to be a number that eventually is going to make the statement true that the average was 80. So the next number, let's say I pick 50. And then the next number, the third person, has even less freedom to vary. It's going to have to be a test score that's going to work out in that equation to make the statement true, the average is 80. I don't know if that makes sense. And I hate that I can't see your faces and that you can't see my face.
It does make sense.
Yeah.
Somewhat.
Okay.
Somewhat makes sense.
It somewhat makes sense, but like, it's kind of like why, I guess, maybe. Let's say number 1, 2, and 3. Or you know what, let's do this because I'm telling you, my brain, I'm not good at math. Let's say that the mean was 50, okay? If the average is 50, and we know that this statement is true and it's never going to change, what number I pick for number 1 has ultimate possibilities. I mean, I could pick 1 million, I guess.
Okay.
Right?
Okay, yeah.
I could. I don't know. I'm not going to do it because I don't know how that would work out. But let's just say I picked, okay, I'm going to go with 100. Okay. Now, the next number, I'm starting to get more limited if I'm going to make this statement true. Right? So let's say I pick 0. Now, my last number right here, it only has one option. I only have one option to make this statement true, right? It's going to have to be.
Okay.
Right. I don't know. I don't know if it's working. I don't know. Oh no, I'm already getting people joining my next class. I don't know if that makes sense. Maybe, just think about it a little bit longer. But that's ultimately what degrees of freedom is. If you don't like this definition right here, mathematically, this is what it is, that each time these spots have less freedom to vary. Okay. If we were thinking of the people drawing the chairs, I think that's a little bit easier to make sense. They have less freedom to vary. Okay. Now let's look at this table here. Okay. I want to write those. So, oh, there we go. Okay. Way up here, we see we have confidence intervals. We'll talk about that in a little, or well, not today, I guess next week, okay? So that's confidence intervals. I'm gonna take that off, okay? Right here, we have, it says alpha level for a two-tailed test and alpha level for a one-tailed test, okay? Now, what they're talking about here is, are we going to look in both tails? This is a two-tailed. And a one-tailed is where we are only looking in one direction. Okay, and it could either be the left tail or the right tail. Okay, now this is where I get a little bit frustrated because it doesn't really make sense until next chapter. But what we are ultimately going to do is we're going to find a number, okay, say in here, that we're going to use as a cutoff point. And anything above or below that number is going to tell us whether we have significant results or not. Okay, and this comes up later in chapter 9, but I just want you to know why I'm talking about this. Okay, so we're going to use these values in here as a way to determine whether we have found significant results. And what we do in statistics or in behavioral science statistics, we go with a 0.05 level, okay? Now what that means is, remember 0.05, if you put it into percentages, it would be 5%. We look at the extreme 5% of the distribution, because we know that the extreme 5% is very unlikely, or it's not probable, right? Remember when we had the distribution, the normal distribution, and I would say that all of this in here is very likely. And if you remember some of my Scribble Scrabble one day where I was talking about the -2 standard deviation and the 2, if you added up all those percentages in there or whatever, it would equal about 95%. So 95% of the population is within 2 standard deviations. So what we're going to look at is the extreme 5% that's left in the tails. Okay. And how we do that, so we're looking at these extreme scores and these extreme scores. When you look at a two-tailed test, you have to divide up that 5% so that you would have 2.5% on this end and 2.5% on this end. Because remember, whatever is equal on one side is equal on the other. So when we do that, now we have, right, we have those extreme 5% that's left in the tails. And this is what they mean up here with the two-tailed test, okay? If we were looking at a one-tailed test, we're only looking at all the 5% on one end. Okay.
Okay.
So this will make more sense. I promise it'll become clearer and clearer as we move along. Okay. So let's look at, if we were going with the 0.05 in the two-tailed, which is right here, it would be this column.
Okay.
Okay, that's the 0.05 for a two-tailed test. If we were looking at a one-tailed, the 0.05 is right here, and you have these values here, okay? Do we see that? Do we see the difference there?
Yes.
Kind of, sort of? Okay. Just at least just looking at where the columns are, right? This one is 0.05. Oops, that didn't work. Oh no, now I erased it all. Oh well. Okay, so we got the 0.05 for a two-tailed and the 0.05 for a one-tailed. Okay. And that's how we will find those values based on whatever our sample size is. So let's say N was 10. degrees of freedom is equal to 10 minus 1, so it's equal to 9. And let's say I wanted you all to do a two-tailed at 0.05, which is right here. What we do is we count down and we find 9 right here. And we just slide our finger all the way over, and that's that value that we will be interested. We're going to call it our well, it's going to be called our critical value, but I'm jumping ahead of myself, but that's okay. Okay, so that's how we find this value. And what that means, let's go over here real quick. Erase all this scribble scrabble. If I had a distribution, oops, looks kind of funny. And let's say on this end was negative 2.262, and on this end is positive 2.262. Those are our critical values, okay? And I know I'm jumping ahead, but those are going to be our points that we're interested in, okay? What these values right here, what they're showing us is that this end and this end is the cutoff for our extreme 5%.
Okay.
2.5% of the people on this end, and there's 2.5% of people on this end. Or I said people, but let's think of it as the probability of an event happening, right? The likelihood of something happening. We only have a 2.5% chance for it to be over here. We only have a 2.5% chance for it to be over here. Does that make sense a little bit better, maybe?
Yes. Yes,
Okay.
it does. A little bit better. Yeah, definitely.
Okay, so we're separating off that extreme 5%. In social sciences, we use 0.05. Okay, it's just our extreme 5%. In the medical field, they use 0.01. Okay, just to give you, and that'll make sense in a little, or I'll explain something. We also always, well, convention and to be more conservative, we use two-tailed. Using a one-tailed doesn't give you as much power. If we look at the one-tailed over here, and let's go with the same, the degrees of freedom of 9, we got 1.833. We know, think back to like our IQ. Is it harder to be over way out here? Or is it harder to be over here? Which one is more likely? If we're thinking of
the one that's like beyond the beyond low, the low like the lowest value.
Okay, I don't know. Well, or maybe I didn't ask it right. We know that this is more likely right here. This 1 point, okay.
Yeah.
It's right, we're gonna have more people here than over here, right?
Yes.
So this value here, this 1.833, even though it is marking off the extreme 5%, it's all the 5% here. They're not even considering this side. They're not even, they're like, we're not worried about that side. They're looking at the entire 5% of the distribution on this side. And so it just makes it like more probable or more likely that there's going to be more people over here, right? There's more of a chance. These are pretty extreme. They're high values. It's going to be hard to get over in those tails. So the higher the number, we know it's harder to get to. If that makes sense. I don't know if that made any sense.
No, it does. It does.
It does? Okay.
It does. Yeah.
Like
That
think
one
of,
does make
right,
sense.
Einstein had 4. He had a value of 4 and he was so far out there, remember?
Yes.
Right, his 4. Look at
Mm-hmm.
this. If you only had a sample size of 2 people, look at their values. You have to, for it to be a 0.05 in a 2-tailed test, you have to have a value of 12.71. I don't even, that would be so far out there.
Yeah.
So
It is
that,
pretty.
so this is where that guy Gossett, who worked at Guinness, I mean, it's like mind-boggling. How did he come up with this? But what he's telling you is if you have a really small sample size, you better have a value that is so far out there that we know for sure it didn't just happen by chance. That you better have a result that you're so sure about that it exceeds 12.71. Okay. And as you look at these values, as your sample size increases, those values get smaller, making it easier to get into that range. Because they know as sample size increases, right, we have more confidence that we are not making a mistake. We have less uncertainty. Okay. Once you get way down here, infinity, if you have such a big sample size, then our value is 1.96. And I never showed you this, but on the normal distribution, you could go back and look it up to find that extreme 5%. Those values, those z-scores are 1.96. And that separates off the extreme 2.5%. And so what is kind of cool about this is like statistics nerds, like really nerding out on this. What this means is if your sample size is big enough, the t distribution becomes the z distribution. And that just kind of like blows, that kind of blows our mind, because like, how did this guy come up with that? How did he know that? But I'm probably way nerding out, and I know I'm going way over. But here's showing a little bit, here's showing that exactly, okay? With the degrees of freedom of infinity, just meaning you have a very big sample size, 2.5% on this side, there's that negative 1.96 t-value score, okay, and 1.96. If you have a degrees of freedom of 9, to find that extreme 5%, our t-values are a little bit higher, right? Bigger, they're scooting in because we have a degrees of freedom of 9. Or sorry, not scooting in, sorry, scooting further, scooting out, right? It's making it harder to meet that criteria of 1.96, made it a little bit further. If you only have a degrees of freedom of 2, that t-value is a negative 4.30. It's separating off that extreme 5%. It's going to be a lot harder to get out in that range, okay? I promise you all of this will make more sense. And I'm going to, next week, we'll go over this. We'll go over confidence intervals. We won't do it right now. But are there any questions based on this today?
No, not that bad. It's not that bad.
Okay, I know it's probably pretty muddy. I know it's not crystal clear, and I do hate that about statistics, but just read over this stuff, look over these, anything that I have highlighted, that I have, bold, just kind of know those, and that's good enough for now, I promise. Okay.
Okay.
Knowing what degrees of freedom is, not N-1, that's it. That's good enough. Knowing what the central limit theorem is, and kind of what these different samples are. And that's it. That's good enough for today, okay? Or this week.
Okay. Perfect.
Okay. And I'm gonna have to go because I have my other class, all right?
Yeah.
But any questions at all? No? Okay.
No.
Isn't that so, I was so annoyed at that it won't let me show my video, but anyways, okay. Well, thank you guys, and I will see you next week.
Thank you.
Okay, bye.
Thank you. Have a good week.
You too.
Bye. Thank
Bye.
you.